Hey guys, hope you're all doing good and welcome to a new video. So today we are going to be working on this supercharger case setup. Now the geometry that I have is quite complex. It contains the solid components, it contains the driving gears, the shafts and also the bolts, right? So our objective is to first understand what the fluid volume here is and try to extract it and then run a simulation. Now this is a made up geometry. So what we will be doing is we will be adding some additional components to it so that the geometry is complete for CFD simulation. As you can see that this is the air side or the air intake. So air is basically going to come in like this. So now this side is basically the inlet, and what I have is I have a very simple image here. This is basically from torquetech.com. We don't own this image or anything. This is just for reference. So here you can see that this is the inlet side and this is the pulley that basically rotates the components inside the supercharger, which is going to help pressurize. The compressed or the pressurized air is basically going to be obtained from underneath of this particular unit, which is basically what we have on this side, right? So the compressed air is going to come out from here. So you can see that this model is fairly detailed, right? It looks very similar to the image. Now usually if you're working for a company that makes devices like this, you are interested in performing a CFD simulation to understand the relationship between the pressure ratio and mass flow rate. That is, for a given mass flow rate, how much the pressure can be increased. And you might also be interested in obtaining the final temperature of the compressed air, because since you're compressing the air, its temperature is going to rise, and if the temperature is higher, the density is lower, and depending on how high the temperature gets, a cooler unit might be required to cool the pressurized air. Alright, so in this particular case we are interested in running a flow analysis. Why? Well, that is fairly simple to do, and that is kind of 90% of the work. I mean, if you're able to set up the simulation for that, then you can look at the exhaust temperature fairly easily. The only thing that you might not be able to do with such a simplified model is understand how the lobe temperatures change because of the rotation, and say you are interested in injecting some lubricant oil, and if you're interested in seeing how that actually moves around the domain, that would require additional setup, which we are not going to be focusing on, right? So the first thing I want to do here is remove some unwanted components. So I'm going to go to boundary, and I'm going to start by flagging or creating a few boundaries. So maybe let's just create like 6 to 7 boundaries. I think we'll need that much. So the first thing that I'm going to do is I'm going to identify some parts that I can delete, right? So that way I can see what's going on inside. So I'm going to be using the surface method. The surface method basically helps you select entities that are a complete surface and are detached from other parts of the geometry. So if I select this pulley, for example, you can see that the pulley and shaft seem to be connected, but if I actually zoom in really close, they are not, right? They are not. You can see that the vertices here don't align, right? So we don't need this particular pulley because we are doing a CFD simulation and this is not required. So how about these guys, the bolts? Yes, there you go, you can select them. So this is the nice thing about the surface option. It helps you select quantities in bulk and quantities that are not connected. So let's just delete it. Alright, so how about this gear? Cool. So it looks like this gear is also separate, so let me delete that, which means this one should also be separate. Now I need to be very careful. I need to make sure that no other components are selected when I do this. So I'm going to go ahead and delete this guy. Okay, so the next thing that I'm going to do is I'm going to try and select the lobes, for example. There you go. So that's the compressor lobe. I'm just going to add it to boundary number 2, and let's just hide boundary number 2 so that we increase our visibility. And we're going to be selecting the other lobe, and let's add it to boundary number 3, and let's hide that as well. Alright, so that looks good. So the next thing that we want to flag is the internal faces. So I'm going to be selecting those guys. I'm going to click on angle method, and I'm able to select this particular portion. And what you can also do is you can do Ctrl+L shortcut key to kind of isolate the selection that you just now made, right? So this is kind of an important region, right? So this is where the fluid is going to spin around. So let me redisplay everything and hide the lobes again. So we need this, we need the back side obviously, and we need the front side, right? So I'm going to add all of them to boundary number 5, and now let's hide boundary number 1 to see what we have. Perfect. So there you go. So that's exactly what you need. So you have your fluid volume and you have your lobes, and I can actually show you the lobes much more clearly right now. Oops. Let me go ahead and hide this guy. Right. So these are your lobes, as these lobes basically rotate in opposite direction, and because they squeeze air, they compress it in the process and they push it around because of the helix, right? Because of this helical structure, they are going to progressively push the air from front to back. And what's going to happen is, if I enable the casing, the compressed air, the normal air is going to come in from the front, and as it gets compressed, it's going to get discharged through this particular outlet. Alright, so what should I do next? Well, I can start by deleting these parts, right? Some parts are not necessary. For example, I can delete this huge boundary, right? So because that contains a large number of triangles. If I delete it, one thing is, you'll notice is that the number of triangles is now really small, and also you can actually move around the geometry quite easily. Okay, so the other thing that we are interested in doing is, you can basically see that the lobes are really close to the casing. Now in real life, they're not going to be intersecting, right? There is going to be a small gap. So here the gap is not very clear. In fact, you can cleanly see that the lobe is actually intersecting with that particular face, which is wrong. So what we will be doing is, we will be moving that face a little bit. So that, and the other thing is, you can actually see that the lobe has this hollow region, which is basically used for the shaft, correct? So the shaft is basically going to go through that. Now, since we are interested only in the CFD simulation, what we can do is, we can basically take off these external components, right? So we need to be a bit careful in deleting these, right? Because you can see that it's clearly selecting some unwanted components. So I'm going to zoom in near the model, and I'm going to see if I can use the arc method. Actually, maybe a better idea would be to just delete this entire face. Right, I can just delete this entire face, and what I'm thinking is, I can just patch it back again, right? That way it would be closed perfectly. So before I do that, I'm just going to get rid of this particular shaft. So I'm going to repair, delete. I'm going to use the angle method. There you go. So I've selected this, selected that, hit the key delete, and there you go. So I've deleted that. Now what I'm going to do is, I'm going to delete this particular face also, but looks like I'm unable to select that entire face. Let me try selecting somewhere else. Nope, that doesn't work. So I'm going to go and create some fences. In fact, let me start by creating the automatic fences, and let's try the boundary fence method. Boom, there you go. So that gets deleted. Okay, cool. So all I need to do now is patch this guy. So I'm going to go to patch, use the open edge method. I'm selecting this guy. I'm going to say auto assign triangles to new boundary, and one thing that I want to do is, I want to say triangulate to specified center point and automatically calculate the center point. So this is a cool feature because it lets you kind of patch it, and there's this center point. This center point is going to be extremely useful for us because it helps us measure the origin and the axis of rotation for that particular lobe. So I'm going to do the same thing on this side. Good, that looks good. And here we need to delete this extra bit. So I'm going to use the boundary fence method. Boom, delete, go to patch, select this guy, hit enter. Oh, okay, I see what's happening. So let me do Control Z here, and I'm just going to delete this particular face, right? So let me go to triangle selection mode by hitting 3, and I'll select this guy, this face, and I'll hit delete D. There you go. And what I'm going to do is, I'm going to go to patch again. I'm going to go back to edge selection mode. Select this guy, hit enter. Select this guy, hit enter. Alright, so that looks pretty cool. What about this one? Would we be able to patch this completely? Well, let's try. So I'm going to be selecting the open edge method. Okay, so looks like that gets selected completely. So let's make sure that we unselect triangle to specified center point. Why? If I do this, it's going to patch, and it's going to try to get those triangles from a particular center, right? So let me first click apply to show you what I'm talking about, right? It's basically trying to triangulate that entire patch so that there is just one center. That is bad because it does not provide any flexibility. Here the hole is shaped in a complex way, right? So let me undo this, and let me uncheck this point, and let's try it again. Click apply now. Perfect. You can see that the patch is good, The only thing is it's intersecting. Well, that is something that we can fix. So what I want to do is, let me just redisplay everything, and let me patch the geometry on the other side as well. And what I'm going to do is, I'm just going to move it till a point where there are no intersections. So I'm going to transform, and I'm going to translate this particular guy, this particular face. Let me make sure that I use selected triangles option. I'm going to use boundary fence method for this, and we are going to be translating it in the Z direction. And let me just enable the bounding box. So here you can see that the geometry is clearly not in the right dimensions. So first thing would be to actually scale it. So let's actually scale it, and then we can come back and fix that particular end. I'm going to scale the entire surface, and what I want to do is I want to scale it by 0.001 because everything is in millimeters, right? So now you can see that LZ is 0.17, so that's about 17 centimeters long. So that's a representative size. Now the geometry is made up, that is why we are having these many issues with it, but that's fine. It's a good learning process. So then I want to go to transform, translate, selected triangles. I'm going to use the boundary fence method, use the Z direction, but put a negative sign so that you're going the other way. And to start with, let's go by 1 millimeter, right, and see where it takes us. All right, so at 1 millimeter, I think we're kind of at the lobe end surface level. Let's do it one more time. There you go. So that looks good. And I'm going to do the same thing on the other side. I'm going to select this guy, and we also want to make sure that we move these guys as well. Oops, but we are unable to select it. So what can I do? Well, it should be fairly straightforward. So let me just select this guy, and I'm just going to translate it along Z direction, and I'm just going to do it once. So that looks pretty good, and I should do it one more time just to be consistent. So ideally, here you can see that the gap size is 2 millimeters, right? Now, how do I actually decide that? Shouldn't that come from the geometry itself? Well, absolutely. Now, in our case, since the geometry is made up, these things are not being taken care of correctly. Ideally, if you're working for a company and say that your client wants you to do an analysis on their supercharger, then they would give you the right geometry. In fact, the work would be fairly less. The reason why we are actually doing this is, this actually helps you understand how you can make modifications to your geometry so that you will be able to run the CFD analysis. So one of the common things that people do is they play with these gap clearances, right? So just to see what happens, right? And in reality, there is no CAD model available for that. So what you have to do is, as a CFD analyst, you need to be able to apply these changes on your own so that you can tell your client or tell your customer what's going on with your simulation. So in this case, I've actually fixed the problem on this side, but you can still see there's one major issue, and that issue is that your lobe is actually intersecting with this outer face. In other words, there's no real gap. So how can I show this to you in a bit more clear way? Well, I can select this guy. I'm going to do Control H so that everything gets hidden, and I'm going to go to options, and I'm going to remove the edges, and we're going to be looking at this, say, along this direction. And if you zoom in, do you see that this particular line is your casing and your lobe is kind of right on top of it? In fact, it's intersecting. So let's go and look at another location. So here you can see that this line right here, that's your outer casing, and your lobe is kind of penetrating out. So this is another problem that commonly occurs, that is, the lobes are a bit oversized. This can happen because of several reasons. Typically, when you get data from a company, these type of issues do not occur. We are seeing these type of errors because, like I said, the geometry is made up. What is the possible solution here? Well, what we can actually do is, we can scale down the geometry so that the lobe is not intersecting with the outer casing anymore. Now, you can ask me if this is realistic. Well, the answer is absolutely not, right? In real life, if you're actually given a CAD model, then you need to make sure that the gap sizes are preserved as much as possible. Only then you are actually running the right CFD simulation. If you are changing the gap size as you wish, then you're simulating some other supercharger. Now, that brings us to a different point though. One thing that people are interested in is to see the effect of these gap sizes on the end results. Why is that important? Well, we all know that if the gap sizes are really small, there is less slippage. In other words, there is less leakage, which means you will be able to deliver more mass flow rate. because the fluid is not going to escape through the gaps. But as a consequence, you can actually heat up the air a little bit more, and that can actually cause thermal stresses on the supercharger components. So one typical study that people do is to look at the effect of gap clearances on mass flow rate and outlet temperatures. And in order to do that, you will be given just a single supercharger, and the objective is to vary the gap size, right? So in our case, we clearly don't have any gap, right? So if you run the diagnosis, you will see what I'm talking about. You can see that you have intersections in all of these places, right? That's because the bowl is just cutting through the casing. So the first step is to make it smaller, right? So how are we going to do it in a systematic way? Well, before I get to that, I'm going to clear this so that the colors are not on the way. And then I'm going to go to view options, and I'm going to hide the casing. And I'm going to be looking at the lobes first, and I'm going to enable the edges. So we ideally want to shrink these lobes, and in order to do that, we can actually scale it, right? So what we can do is we can go to transform, we can go to scale, and then I can scale the selected surfaces or selected boundaries. So let's select selected boundary options, and I'm going to be selecting boundary 2. And for scaling factor, what I'm going to do is I'm going to scale it to 0.99, right? So I'm just reducing the size of the geometry by a very small amount, by 1%. But the problem is I'm being asked for a scale origin. Why is that important? Well, if you don't give the right scale origin, what's going to happen is, and I can kind of show this by exaggerating the scale factor to 90%, right? And let me just click apply, right? So you can see that the geometry is getting scaled down, but there is another huge problem. As it scales down, it is also moving, right? That's because the scale origin is set to 0, 0, 0, right? So that's bad. We ideally don't want to change the positions of the lobe. We just want to shrink it exactly where it is. So let's do Ctrl Z 3 times so that we recover the original geometry. The key thing is to actually set up this scale origin correctly. Well, what would be the right scale origin? Well, that should be the center of this entire lobe. And to do that, what I can do is I can just go to measure location, and I'm going to click on this front vertex and this end vertex. Well, to do this, I'm going to go to measure, and I'm going to location, and I'm going to select the front vertex, and I'm going to select the vertex behind and click apply, right? So we have this particular point. So let's copy this guy, and let's go to transform scale. We are going to be selecting the same guy, but this time I'm going to paste this new point, and for demonstration purposes, we'll still have 0.9 as the scaling factor, and let's scale it down. You see that it scales down, but it hasn't changed its rotation axis, and that's very important. So let me just undo this 2 more times and just look at the geometry from a couple of views to make sure that the lobe sizes are completely the same. So in our case, what we are going to do is we are just going to enable the casing first, and we are going to apply 99% scaling factor. And we're going to do it only for boundary number 2 first. We click apply and run the diagnosis. You can see that this side there are no intersections, so that's great. So that means whatever we did is perfectly fine. The next thing that I'm going to do is I'm going to scale it down on the other side. So for that, I'm going to go to measure, location. I'm going to select this point and this point, click apply, select this guy, copy, go to transform scale, and put this as the new scale origin, and this is going to be boundary number 3. So let's click apply. You can see that boundary 3 got reduced in size. Let's run find, and you can see that now you just have open edges and normal orientation. So that basically tells us that we have fixed our geometry problems. So that's pretty nice. So how about these minor issues? Well, they can be fixed very easily. So I'm going to go to repair patch, and I'm going to select this particular open edge, and I'm just going to hit enter. So that has been patched. Now what about these guys? Well, I can just patch them by just selecting. I'm just going to assign them to a new boundary, and then I'm just going to remove this auto assign boundary for new triangles feature and click apply. And we're going to do the same thing here as well. So this looks bad. Okay, so let me do undo, and what I'm going to do is I'm just going to go to patch ordered vertex list, and I'm just going to select these 4 points, actually 6 points, so that I can help Converge Studio. And for this, I'm just going to go back to this particular option so that the boundary flagging is done correctly. There you go. So that looks good. Now let's go back to patch, use the open edge method. We're going to select this guy and we're going to uncheck this option. We're going to click on apply and let's run find. So normal orientations are gone. We still have open edges. I need to see where that problem is. So let's fix the normal orientation issue. Go to transform normal and click on attempt to fix all normals and click apply. Let's run find. You can see that that problem is gone. You still have 9 open edges right here. Okay, so I think the problem is that we might have missed an edge to patch. We might have missed a small triangle. So what I'm going to do is, there you go, you can see that there's the small triangle. So let's go to repair patch, select this guy, enter, click on find. Looks like we have a few more. Let's select this guy, click apply. So we have isolated triangles, that's easy to fix. So I'm going to go to flag, I'm going to select the casing and I'm just going to select these 2 triangles and click apply and hit find. We have one more isolated triangle, so let's just click on show. So that clearly belongs to boundary number 5. So I'm just going to select that and click apply. There you go. So our geometry flagging is complete. So with that I would like to finish this particular video. In the next video what we will do is we will adjust the inlet and also the outlet portion so that it looks like a more realistic setup, and then we will assign the boundary conditions, the mesh, and the usual drill. Alright, with that I would like to conclude this video and I'll see you in the next one. Bye. Hey guys, hope you're all doing good. So I just wanted to change a couple of things with the output and post processing. So let me first go to output files, and then what I'm going to do is I'm going to enable generate wall boundary averaged output, and then I'm going to go to post variable selections, and I'm just going to make sure that I enable a few parameters. So we're just going to enable this volume guy, and then we're going to go to combustion turbulence and we're going to enable Y plus, and we're going to enable ratio of turbulent viscosity and click on OK. Alright, so now we are ready to run the simulation. Thank you. Bye.